Alright, so here's an interesting IB Math IA idea that helped many of my students score 20 out of 20. Here, two drones are flying through the same airspace. Their flight paths may cross each other, but will they actually collide? This single question leads us to one of the most elegant applications of vectors and skew lines in IB mathematics. Here we have taken two drones, drone A and drone B. Drone A is moving along the blue line while the drone B is moving along the yellow line. And this is the top view of the routes of the drones. It seems as if the two lines would intersect each other. But if they are really intersecting, then the drones might collide in real-time scenario, which we don't really want to happen. So now let us dig deeper into it. Now here's the side view of the situation. Drone A is moving at an altitude of 10 meters straight without climbing upwards, while drone B is starting at a lower altitude and it is steadily climbing upwards. The previous animation gave us the top view of the situation, while this animation gives us the side view of the situation. Now let us try to see the routes or the lines along which the drones are moving in 3D. So we can see the routes of both drones A and B, they are actually neither parallel nor they intersect. Such lines have been given a special name known as the skew lines. Now, if these lines or the paths or the routes of the drones are not intersecting, then let us try to figure out how close do these drones come. Let us quickly calculate the shortest distance between the two drones. So for that, we'll first write the position vector of both the drones. As we know that position can be written as initial point plus scalar times the direction along which that particular drone is moving. We are here denoting the position vector of drone A using RA. So now RA vector, that is the position vector of drone A, is written as A naught vector plus some scalar times D1 vector, where A naught vector is the starting point for the drone A. Here we are assuming A naught to be as 0 I cap plus 0 j cap plus 10 k cap, and the direction along which the drone A is moving as 2 I cap plus j cap. Similarly, we can write the position vector of drone B as B naught vector plus some scalar times D2 vector, where we are assuming over here the starting point of the drone B as B naught vector equal to 3 I cap minus 2 j cap plus 9 k cap, and D2 vector, that is the direction along which the drone 2 moves, as I cap plus 2 j cap plus k cap. Now we know that the shortest distance between two lines will be along a line which is perpendicular to both the lines. So here that is being denoted by n vector. So how do you get a vector which is perpendicular to the two given vectors or the two given lines? Using the cross product. So this n vector can be written as d1 cross d2 vector. Now d1 vector and d2 vector cross products we are setting up in this determinant form ijk210121, and finally we are getting n vector as I cap minus 2 j cap plus 3 k cap. Finally, let us take projection of AB vector onto n vector. This projection is going to give us the closest distance between the two drones. Now using the projection formula of one vector on another vector, here the projection or the closest distance would be given by modulus of AB dot n vector over modulus of n vector. Now what is AB vector? AB vector is position vector of B point minus position vector of A point, and n vector is as we had calculated earlier. Taking the dot product and taking the modulus, we have the projection or the closest distance as 4 over root 14, which is approximately equal to 1.07 meters. Now this is the closest distance between the two drones. Therefore the two drones will never collide with each other. Let us discuss a few variations to our model, that is sensitivity of our model. What happens when the drone B's initial starting point is changed? Let us assume that the initial starting point of drone B is 3i minus 2j plus zk cap, and we'll do all the calculations again. That is, we'll calculate the projection that is closest distance, and it turns out to be 3z minus 23 over root 14. Initially, we took the z coordinate as 9, and if you plug in z as 9 over here, we'll get the same value as 1.07 meters as the closest distance between the drones. Now, why is this calculation in general is important for us? Because with this, we can figure out that the closest distance will also hit 0 when this numerator 3z minus 23 becomes equal to 0, that is when z is 7.67 meters. Therefore, the initial starting point of drone B's altitude, if it is 7.67 meters, then the drones will collide with each other. Therefore, we can conclude that the initial starting point of the drones do play an important role in determining whether they will collide or not. Let us discuss another variation to our model. Initially, our drones were moving along non-intersecting lines, but then there can be situations where drones are moving along intersecting lines. For example, here I've taken two roads which are crossing each other, but the cars aren't colliding. Why? It's just because these cars are crossing the intersecting point at different times. Therefore, time will be also one deciding factor which will predict whether the drones will collide or not. Further, I have listed down the improvements which we can do to our model, and as well as the assumptions also I have listed down over here. So if you are an IB mathematics student aiming for a top grade, then this channel is where you'll learn how high level mathematics solves real life problem. Thank you.